So probably in the chemistry you would all uh, talk what is the electron in a potential box, and we may know uh, what after that it happens. Why we are not taking when we teach a student, we probably will start with quantum chemistry or quantum physics with electron in an infinite potential well. Very rarely people will touch with the finite potential well too, because solving the problem in the class is not easy mathematically. It needs computation, especially in terms of finite, or you have to give the finite energies and so on. What happens if more than one electron present in the potential well? That is also a topic of we won't touch most of in the classes. But actually, that is the case in the solid. So when two atoms comes nearby, there will be interactions between the electrons and the neighboring atoms in the lattice that lead to many more complexes, which we rather we have to mathematically we cannot solve there in our hand mathematics. We need tools to solve, like softwares and programs. I just start with a simple case. We all know what is mean by linear combination of atomic numbers, and no need to discuss much more in this. Just when two hydrogen comes nearby, we all know the orbitals will overlap together, and that due to the interaction of one hydrogen nuclei with the other, and one electron other from one neighbor to the other, as well as the one nuclei with, suppose this is A, this is B, the nuclei of A will attract the electron of B too. So this will alter the energy levels, and based on that, we know that there is a bonding and anti-bonding orbitals. And when we represent this in terms of wave function, we used to teach the students by means of superposition principle. So just to these are superpositions of two wave functions of oneness orbitals for sigma bonding. Just their safe for electron distribution around the bonding. So just move on. When what happens is when we take a isolated atom, for example, in the case of hydrogen, it has only one energy level. Say, for example, when I bring two hydrogen atoms nearby, then the oneness starts to split to bonding and anti-bonding. This is a fundamental what we teach to students, and we all know the energy of this level can be calculated by solving the Schrodinger equation. That needs a lot in the case of when you say a molecule, the interaction is very simple. But when you want to calculate actual cases, not with the minus 30, minus 50, what we do, we have to how to incorporate the interaction between the two atoms, the potentials. In 1950s, these are much more example, and what we call as a density functional theory gives us a solution to how to accurately calculate the energies of these electrons when they are involved in interactions. So just I skipped this. Just you all know about what is the bonding energy level and anti-bonding energy level, how they are greater. So moving from hydrogen to helium, in this case, if you see the same possible, you have a oneness electron. You have both the sigma bond here, and bonding and antibonding, where you can see the antibonding states are not empty as hydrogen, and see the filling of electrons in the highest states. But helium bonding doesn't exist. We all know that. So it depends on their overall energy. Overall energy is greater than two isolated helium atoms. So helium doesn't have. If you have the same thing, if they take, for example, a ABC atom put together nearby, then their wave functions overlap both with the symmetric and anti-symmetric case. In the case of symmetric, they have multiple possibilities. With a superposition, they can be added, or there can be difference between them. And anti-symmetric case will form the difference between them. So overlapping orbitals can form in different ways. This leads to different energy, and this will give us a different branch out from their isolated form. And slightly, when we move to these molecules to a solid, what happens to the solid? The atoms are close further, so the interaction is much more. So in the case, if we take a lithium, which has a 3 electron system. So you have a 1s filled and 2s1, and when two lithiums are separated by a lattice parameter A, their interactions will lead to a 1s level into splits into a branches of letters, and this we refer as a band. And the bands, usually the splitting, we all know by Paulo's exclusion principle, two electrons can fit into a single energy level, so they will be degenerated. And when we move on, this S itself will have an empty set. Similarly, when we move on to 2p, already we know that they are not filled and they will be empty. This forms the conduction band. So when we have a filled orbitals, the lower filled orbitals will form the valence band, and in the case of lithium, the 2s unfilled will be a lower part of the conduction band as 2p followed by that. So when you move on from 3 electron to more, this energy levels when starts to be there, this splitting will be more, and then branches will be in such a way that the S and P will merge together. So the interactions mainly, we all know, it depends on the overlap, and primarily we say overlap, but it is a charge overlap. Rather than we can't say the electron will revolve on the same distance. A charge density overlap that leads to interactions, Coulombic interaction between them, and the potential be created due to the interaction will lead to these branches. When it comes to the topmost orbital at 0 Kelvin, in metal we used to refer as Fermi energy or Fermi level. In terms of chemistry, some cases we used to refer as a chemical potential too. Then move on with this with the actual the theoretical band structure calculations based on DFT. We used to teach like this in the terms of boxes, where one of will split into a branch like followed by say 0.5 to 0.6 Brownian. Whereas in the 2s, 2p, 3s, the Brownians will move. And if you see that X orbitals will branch out to be more than P and D and F. For example, you can see here, I showed a copper band structure here. The 4s orbital of the copper has an energy level ranging from -4 eV to of minus nearby 8.5 eV. Around like 4 eV, the width of the band will be. The same case, if you see a 3D band, the 3D band will be rounding will be there around 2 eV. So what does it have? Basically, we have to understand about reciprocal lattice and then zone. We picturize this band structure in terms of reduced zone. This reduced zone is nothing but when you are moving, the electrons are moving, they are not the acidos. So when you include the motion of the electron along the x-axis, then these pictures will be there. Depending upon the direction of movement of the electrons, we are picturizing in terms of energy, purely theoretical, and we say this is a wave vector, though this gamma represents the center of the Brillouin zone with a 0, 0, and x is 1, 0, 0 direction, and so on. So for make it easy, we used to say that top-filled in case of metal as a Fermi level. In the case of insulator and semiconductor, this will vary. Let me move on to semiconductor in the same case. Let us take the silicon with 14 electrons. It has 1s to 2s to 2p6 and 3s to 3p2. And here, an isolated silicon will have 3s2 and 3p2 configuration. But what happens is when we bring two silicon nearby, due to the Coulombic interaction between them, there will be sp3 hybridization will take place. The electron energy of 3s and 3p, as we already seen, when these electron interaction with the nucleus, the energy levels will branch out, and these branch outs will make sure that they will overlap. So there won't be a much difference between 3s and 3p, and then the chemistry will say that is a hybridization takes place between these energy levels. So there will become 3s1 and 3p3 half full, which is become stable one, and in turn it starts to bond with the other 4 silicon in the unit cell or in the lattice to fill the entire orbit and become much stable and forms a say covalent relationship between them. So what it leads to? This leads to the filling of valence band, and there is a empty gap or forbidden gap between them, and then unfilled allowed conduction band elements. So the unfilled 3s and 3p forms the bottom of the conduction band, and we all know what is valence band, 3s and 3p, or the 3s1 and 3p. This band is the s orbital, 3s, whereas this is the 3p. So this will be pictured in boxes like this. And here again the unfilled S forms the bottom of the conduction band, and the P here, this one, will have the 3p of conduction band here. And at room temperature, the band gap is 1.1 eV. I don't know, in the 0 Kelvin, theoretically it is 1.18 eV. So we can classify, as we see in the case of conductivity, we can classify based on the energy levels the materials into conductors and insulator, as we already seen in the case of lithium, where there is no gap between the bands. Even though the gaps will be there, that will be in the top of the conduction band, where some parts of conduction band, not at the valence band and conduction band merging. So we say the bands are completely filled, and there is no band gap visibly near the valence band, where the bands will overlap. That means the band gap is 0. We call them as the metal or conductor. In other case, when there is a sufficient band gap from 0.1 eV, and there is no categorical difference, they have put less than 4 eV. Now even some of the like silicon carbide and more wide band gap temperatures come into picture. This slightly varies. The scientists differ in the book. Previously it was 3 eV, but once the 3-phase semiconductors like gallium nitride, zinc oxide, 26 comes into picture, this was just enlarged up to 4 eV. So the band gap of up to 4 eV, we can record this as a semiconductor, and whereas greater than 4.5 or 5 eV, we used to call that as insulator. And a perfect example is the silica, whose energy is greater than 9 eV. So just I showed before the first slide about the conductivity. This comes with respect to different materials. The conductors, the category starts from 10 power 3 to 10 power 12 and so on, though we know that possibility of infinity current possible in the case of superconductors theoretically, but practically there are restrictions there too. Depends upon the current density, that has the limit, depends upon what superconductors you are doing. And in the case of metals and metals alloys, mostly we have like a nickel, chrome, silver, platinum. Those forms have greater than 10 power 6 Simon per meter. And some of the semiconductor, as I mentioned earlier, depending upon the high percentage of doping, we used to call them as a degenerate semiconductor, where due to the dopants comes close to each other, and they will fill the bottom of the conduction line, so they are readily conduct. So they have a conductivity nearby 10 power 3 Simon per meter. And other we have seen, elemental semiconductor normally will have in terms of -3 order, whereas the compound will have gallium arsenide, you also will have in -6 order Simons per meter. In the case of ceramics or insulators, we have 10 power -7 or less than that. You can see up to the 10 power -18. In between, you can see some polymers. As an insulator, even our wires, we are using polypropylene wires and others as an insulator. Their combinations to be found. But if you see, there is also a conducting polymer which will not be as in the range as in the case of conductors. Still, they will be falls along in the range nearby semiconductor to insulator. Still, we regard them as a conducting polymer, and considering their insulating range before. And what is the difference in the case of metals? Still, there is a much applications for this. It depends upon the density. The amount of material what we use in the case of metal and the amount of material that has been employed in the case of conduction of polymers is very, very small. Okay. So further, based on the band structures, the semiconductor can be classified in two types. One is a direct band gap and indirect band gap semiconductor. So here there are two pictures where we are aware of silicon and germanium in the case of elemental cases. If you see the top of the valence band, to be frank, in the center of Brilliant zone, that is gamma 00 direction, forms the maximum of valence band in the case of silicon, whereas the bottom of the conduction band comes along the direction of 100. So the electron has have to take a change in direction when it comes from the conduction band to valence band. So like just you are crossing a road, if there is a pathway of road crossing straight away, you will cross the road straight away. Whereas if we want to take from east to from south, way of direction change, that change will be there because the conservation of momentum will be there in the transfer for electrons from conduction band to valence band. What does it does? It restricts the use of this semiconductor to certain applications only. In the case of gallium arsenide, which is a compound semiconductor, you can easily see that the valence band top and the bottom of the conduction band lies in the same 00 directions of the line zone, or they're in the same vectorical directions. So they forms a direct band gap semiconductor. Whereas the silicon, or in the case of germanium, they forms an indirect band gap semiconductor. So what the properties got restricted? This when the electrons are excited, when they comes back, they can't come back directly. They have to move to some other energy level, which has, say for example, the direct band gap in silicon is 3.4 eV. So they have to spend more energy to go to 3.4 eV. Then theoretically they have to come back after that. So there will be not when there is a electron from high energy to lower energy transition, it has to emit the energy, and mostly it will be a radiative transition in the case of direct band gap semiconductors. Whereas in the case of indirect band gap semiconductors, it's not radiative, it's a phonon transition. And during their transition, there is the excited electron will recombine with the hole which is being created in the valence. Like we all know, in the case of metal is a unipolar conductor, whereas in the case of semiconductors, it is a bipolar conductor where electron and hole will be there. The whole movement will be in the valence band, whereas the electrons will be in the conduction band. In the case of schematic diagram, we can say throughout the solid, the electrons will move wherever, whereas the electron migration in the valence band or bonding will lead to a hole movement. Just like that, we take a water bottle and fill the water bottle and drink a small water. It creates a bubble in the water bottle, and if you move the water bottle upside down, the bubble will move. But what actually happens is the electrons is the water is moving, the air bubble is seems to be moving fast. The same case in the case of pole movement, where the electrons migration within the, or we say hopping, the hopping mechanism between the electrons in the valence band lead to the pole movement for us. Okay. So then further, for application point of view, when you see a pure semiconductor, which is say we used to call this intrinsic, where the number of electrons in the valence band will be equal to the number of holes in the conduction band at any time. We call that as an intrinsic semiconductor. It is an ideal way of definition. But in reality, we know that we can't have be in an ideal world. There will be defects that leads to not an equal distribution of electron and holes in the respective bands, but the defect levels will be there within the band gap that lead to some carriers. So the order of carriers will be very, very less. It will be in the case of silicon, if you say intrinsic, the practical way, if you go a wafer using Socrates technique and you measure it, it will be on the order of 10 power 10 per centimeter cube. That too, the compound semiconductor will have an advantage where you have the same multi-growth. If you grow a compound semiconductor like aluminum, you check for intrinsic or carrier concentration, it will be in the order of 10 power 6. Then for applications, we don't have sufficient carriers, though we need semiconductors for electronic applications. The carriers will not be sufficient, so we have to change the order of carriers in the intrinsic. So when we do that, we call that as an extrinsic. By when we introduce the foreign substance into the parent of silicon or germanium, we say the impurities are added. So it becomes an extrinsic. What it does is it will change the polarity of the intrinsic behavior. Most cases, like elemental semiconductors, the native polarity will be negative, that is the electron rate. So when we say an extrinsic, we select a proper substitution of elements such a way how we need. Suppose if we say a p-type, we need excess of holes, then we add an element such a way that 1 or 2 valency less than the host semiconductor. So this leads to electron less in the bonding that creates a holes in the valence band. That's why we say excess of holes reference to the native semiconductor. In the other case, if it is an n-type where there has to be excess of electrons, we choose a dopant such a way that a substitution dopant such a way that it has additional valence electrons. There is extra electrons in the electronic particle or valency which will be higher than the host. So the most way when you ask the students, you will say when you take a silicon, if you add a 3 or 4, 3 or 5, it will change the character. But you will not tell the answer of silicon or germanium when you say p-type and n-type. So that is not a generalized way of defining. You have to create an excess of electron in the case of n-type and excess of holes in the case of p-type. Like to start with, if you take an n-type, in the case of silicon, as we are aware of sp3 hybridization and covalent bonding, the arsenic will have an extra electron. What we have to understand is when there is a substitution in the latter, the arsenic will be asserted and the extra electron, which doesn't involve in the bond, will move around the arsenic. It will not be localized from the arsenic. It is a model actually to consume the creation of and in the energy levels in the band gap or inside the band gap. So this electron has an energy. We call this as a donor energy level that will be mostly nearby the conduction band, and the dopant will be used in such a way that the energy between the donor energy level and the conduction energy level will be minimum, which we will refer as an ionization energy. We all know what is ionization. So here in this case of arsenic, in silicon it is around 45 milli electron volt. So whenever the arsenic gets some energy to get ionized, that means this electron which revolves around the arsenic, even though it is doped, when it get delocalized, then we say that electrons from the donor energy level will move to the conduction band. Since this is in terms of milli electron volt, the order of room temperature is around 280 milli electron volt or 280, depends on the temperature we have. We say in the Kelvin, it is around 280. So this energy will be sufficient for the movement of the electron from here to the conduction band. So this will lead to conductivity in the case of arsenic. And the order of doping, this scheme of diagram is shown in such a way that 1 ppm of arsenic is doped in silicon. For that means 10 power 6, for every 10 power 6 silicon atom, one atom is being replaced with arsenic. In the case of p-type, if we take a boron which has a lesser one electron compared to silicon in terms of valence, if you see there is a non-bonding will be there from the silicon to boron. That leads to what we call as a hole in the valence band. So this bonding electron will not be a part of valence band. So this creates an energy level. So we all know that energy level cannot be drawn for an empty hole. So the acceptor energy level is formed due to the other electron which is there. So whenever there is a electrons comes migration from here to here, this from neighbor bonding, we say the electrons are shifted towards the acceptor level. This hole will be created in the valence band, and this leads to conduction of holes in the valence band. That's movement of holes in the valence band, and we used to say the positive charges starts to move. Actually, the electrons is moving, but we refer as the positive charges in p-type. Okay, this is all about elementary case which will be in the textbook. But when you move from compounds, from elemental to compound semiconductors, the trouble starts. Why? If we take technologically, what we use much more in the case of LED lasers, even in solar, the 3-5 dominating 3-5 compounds after silicon and germanium. Their bonding is also sp3 hybrid orbitals, but it is the way it bonds is different. It's not purely covalent like elemental semiconductor. The bond will create or it has its own ionic formula too. As a chemist, you all know that the arises due to the difference in electronegativity between the elements that being there in the 3-5. The table which I been showing here has the part of compound semiconductors in various groups. Say, for example, if we take gallium and arsenic, the difference in electronegativity is around 0.4. So this leads to the electron means being pulled towards the arsenic case. So there will be a little ionic character will be there in the case of arsenic as well as gallium. Basically, we form 3-5 semiconductors by using gallium arsenic, gallium phosphide, gallium nitride, gallium antimony. These are the famous ones starts in 1980s. As I told, the indirect band-gap semiconductors lacks the light emitting property. So when you need an LED or laser with a high efficiency, we have to move on to a direct semiconductor. That comes the compound semiconductor, also mentioned gallium arsenide, gallium phosphide, and their combination of alloys will lead to different colors of emission today what we have or what we are buying for 2 or 3 rupees in the market. And other compounds also being tried, especially the 2,6 is being hyped as 3-5, or since the material availability is much higher in the case of 2,6. But other than specific like cadmium telluride, other things is not comes in the market in terms of semiconducting property. Zinc oxide and zinc sulfide and other things are there for some other application like sunscreens, medicines, and so on. Not in the electronic or optoelectronic applications. Gallium nitride is mostly used in the case of solar cells and then silicon, or second generation solar cells. If you see that, too the covalent character, apart from covalent, there will be ionic character, and there is also a semiconductor with a 4-4 group, so carbon-carbon or silicon germanium and silicon tin cases. So when we say doping, like elemental cases, in the case of compound 2, it is achieved by introducing specific atoms which intend to substitute the host lattice. Like for the 3-5 semiconductor, if principle group 3 elements, if you replace by group 2, the old periodic table, then it produces acceptors in group 2. The same way, if you replace a 5th element by a 6th element, it plays a donors. But in reality, there are n number of possibilities. There is no general rule for optimum doping. So here I refer few old semiconductors, compound semiconductors, which being just later. So if you say gallium arsenide, the N-type behavior can be done by choosing a dopant like tellurium or sulfur by substituting it in the arsenic site or in the arsenic lab. The same thing, you can take a silicon and germanium, and if you replace gallium, you can have the same excess electrons or N-type character to gallium arsenide. These are industrially used during the night. In the case of P-type, if you take a zinc or chromium and if you substitute gallium, then it will show a excess holes or P-type character. Whereas if you take a silicon or germanium or the carbon, and if you replace arsenic, then you can have a P-type. Then there comes a challenge. How to specifically locate the site in terms of growth? There comes the growth or extinction procedure. You have to have a lot of variations, and you have to optimize a particular condition. Say in the case of, say for example, in the case of gallium arsenide, it depends on the temperature too. If you move on to gallium nitride or any 3 nitride, gallium nitride, indium nitride, aluminum nitride, you can take mostly the silicon for substituting gallium, and germanium for substituting gallium will be better match for N-type. But the nitrogen will not be targeted much as in the case of arsenic for taking a N-type character or as a P-type character. In the case of P-type, you can take a magnesium and it will show P-type, and there is a challenge because of higher ionization energy for gallium compared magnesium is higher energy relatively compared to gallium. So the challenge of P-type doping in gallium, but now it is interestingly established now. And why nitrogen is not targeted, most of the gallium nitride is not grown as a high bulk structures, it's grown in epitaxial layer. So mostly the ammonia is the precursor for nitrogen, cracking ammonia, react with the gallium at a higher temperature, the order of 900 degrees Celsius. And more, if you take aluminum, then you have to go more. And in the case of indium, you have to come less. And in the cadmium telluride case and zinc oxide, you can take aluminum for N-type and indium one and phosphorus potassium. In the case of here also mostly the target will be cation for any process. Now most the anions also being targeted, like chlorine or iodine for having an N-type character. Taking the zinc oxide as an example, all the metal oxides have different characters, not like other compounds. Other compounds tend to oxidize, whereas this they will lack oxygen. Even though we say oxide, the stoichiometrically they will not fill. That means Zn50 and oxygen should be 50. It won't be oxygen 50. It will be oxygen 45, 46. Depends on the group. So this native oxygen defects will create a impurity level in the mantle, and mostly it is an N-type character. So whenever you take a zinc oxide, if you want to make a P-type, it is very challenging. Even though a lot of patents are there, and industry started in the US and they closed competing 3.5 and 2.6. I think 2.6 devices are not come to the market because of the lack of P-type stability in the P-type. And since I told no general rules for optimal doping, then let me take two types which we used to call amphotic doping and isoalcoholic. What is amphotic doping? I'll deal with an example for easy understanding. Say a compound substituted gallium arsenide. If you take a silicon and dope, the silicon has the possibility it can replace the gallium as well as the arsenic because the size will match with both. So if you replace silicon with the gallium side, you get a donor. Four, one more electron will be there. At the same time, if you replace silicon in the case of arsenic side, you will get a acceptor. So this we use for amphotic doping, where same dopant can be used to create two types of characters. Then how it will be done if I need a P-type or N-type, what do you have to do? I have to optimize in the case of growth conditions. Usually the acceptor impurity has to be done in the case of high temperature, say 700 or 800, in the case 900 grade or vice versa. The case of isoelectronic doping, it's the same thing. If I take a gallium phosphide semiconductor, if I replace with nitrogen for phosphor, there is no change in much in the valence. So the electron configuration, this is isoelectronic. So there won't be any change in the character of polarity. That means the charge density doesn't change. Then what we will do? It will change other behavior, like in the case of recombination behavior, it much influences. And if you make in terms of higher doping, let's say alloy, you can change the band gap. So this is the schematic way where from moving to metal, if you see the semiconductor, in the case of intrinsic, though in the ideal case I have shown, we have defect levels in the band gap, and we refer the work function as the energy level for Fermi level to the vacuum level. That means the electron when it moved out of the material, we say that is the vacuum level. Or in the case of semiconductor, we refer in terms of affinity, electron affinity. We also take into account like Fermi energy will be fixed in the case of metal, but Fermi energy in semiconductor is purely a imaginary thing. There is no electron, actual electron will be there in the Fermi level. So we take electron affinity when you want to compare the band structures for different semiconductors or with metals or different materials too. So if you create an N-type, we all know the donor energy level will be created. So the Fermi level, what it here refers is only a probability of finding the carrier in the band structure. So in the intrinsic case, the probability is of whether you can find the electron in the conduction band and the probability of finding the hole in the valence band is 50%. So you find the Fermi level will be in the middle, nearby the middle, not exactly at the middle, nearby the middle of the band. Whereas in the case of N-type, the probability of finding the electrons is near to the conduction band, so you can see the Fermi level will be located near to the conduction band. As in the case, in the P-type, you have the probability of finding the hole will be there in the nearby the valence band. You can see the Fermi level will also lie nearby the valence band. So with this, we also know how the p-n junction is formed. Just for a flavor, I just take two types, P-type and N-type, with the other marking of their energy levels. Here EI refers to the intrinsic Fermi level, and the Fermi level for P-type, and En refers to the Fermi level in N-type. So when we join two semiconductors, just not like a sandwiching, we have to grow proper way to form a smooth interface. We can take, suppose if I take a I2O plate and just place a semiconductor of p type above that, we can form sandwiching of p and n. But the interface will not be smooth. That lead to the movement of the carriers much more resist in the interface. They can bounce back to the same material from, say, for example, a p type 2, it will not move to the n type, it can come back to the p type itself. So the growth process is more important when you form a junction. It's not like a sandwiching doesn't mean that you take two and attach. Either we do in the case of lab to form or to understand about whether there is a p-n junction is being formed. In general, we refer this as the heterojunction 2 or an interface. So when you join, what happens in terms of band structure? Like we can take the Fermi level as an imaginary to be a water level. If you take a two water bottle with the different levels, and if you join two water bottles, then what happens is water level will flow from higher level to a lower, and unless the two levels are same. The same thing will happen in the case of electrons too. When you join the energy, at the place where there is an interface is there, the electron starts to move from an n type to p type. So this leads to lifting of bands actually. So the Fermi level will, unless until it became normalized, there will be a movement of electron. That diffusion will take place from the higher concentration to lower concentration, and it will continue until there is a opposition from the depletion region. So once it starts to move the carriers, the interface will depleted of charges, and we call that as the depletion region. Say in the case of n type, if you say more arsenic is dope, so the electron from the arsenic will move to the p type. Okay, so the arsenic ion will be a plus. So when the hole comes, there is the whole movement from the p type comes to the n type, the ion will pass to it, will resist the movement, or it will oppose. That region of ions present, that is not a movement, that is substituted ions in the lattice, presence in the interface forms space charge region. That will create a potential in the space charge, where we often refer to the students as a built-in potential in the intervention. So this built-in potential can be understood in terms of energy levels too. The difference between the energy levels of the conduction band of 1 P to n. That forms a barrier. We often refer to as a barrier for the movement of electrons from n to p. In the case of holes from along the valence band, the reverse way of understanding the hole will move from, in the terms of here, it will be easy to move from lower to higher rather than from higher to lower. So these are some basics of what we say space charge region, and how the electrons and holes evolve. And we always understand that the conductivity will be a constant throughout the length of the semiconductor junctions. Only in the junction, the conductivity of holes or electron will vary. Once you move far away from the junction, then the concentration will remain as previous. So if I take a 3 micron silicon wafer, and if I start to dope with say already there is a p type, and I am compensating and doping with a n type. The dopant region, if I dope along 1 micron by implanting, so the width probably it forms around 0.5 micron at the interface, and after the 0.5 micron on the either side, it will be the same NMP. So width of the junction, depletion region, is more important when you go for a heterojunction devices. Okay. So let me take. I think I took more time in this case of basics. Let me move on to the devices. Let me restrict myself to a photo director. There are basic characters response for a photo director. Which is sensitivity. Sensitivity should be depends on the wavelength. What are the wavelength the director has to be sensitive, and efficient conversion. That means the photons have to be absorbed and efficiently converted to the electron, and how fast is response, And whether there is a background thing, that is if there is a defects more, then they will also contribute to the electron movement in the devices that will create noises during the measurement. So if it is a low intense light, this the noise this will be more, then our detector won't work. So low noise detectors has to be applicated, and then the area of the device, and then reliability. If I use now, if I use after 1 year or 2 years, it has to be the same. That should be only small percentage of variation should be there, and finally the cost of manufacturing. So here, most process in the, as my topic is solution process, if I say all this, the sensitivity, efficient conversion, response, and most nowadays the all we can take. Only thing is in the reliability and low cost will be good in the case of solution processes, can be easily extended to large scale. But there are reliability and then the efficiency slightly not up to the point of other high efficient like chemical vapor deposition process. So generally, if you take a photo detector, all depends on the absorption, how a material is effective in absorbing the light. And each material has its own absorption capability, and it depends, we say a parameter called absorption coefficient, depends on the medium. Whenever there are photons, this is the photo generated current, the relation shows how the photo generation, theoretically, we can tell the photon current in the case of semiconductor. P naught is the optical power that is incident on the semiconductor, and here the material what we have to rely on the absorption coefficient. Whenever there is a high absorption coefficient, then the amount of material you can use can be reduced. So these are the famous up to date what we have a detector in the case of TV and other devices what we use domestic also. Mostly if you compare photo detector, germanium has more efficient than silicon. So if you see the absorption coefficient will tell that why the germanium is more efficient than silicon. The absorption coefficient for the wavelength from 1.8 micron to higher range of energy up to 0.4 micron. The germanium will dominate the silicon. Even the compound semiconductors will have the moderate rate when you compare this germanium detectors. So now the modern thing, whether we can able to produce this silicon or germanium solution process devices is very challenging. So far, we can't have a device with a solution process silicon and germanium things. But that lead to different exposed for different materials. Then the gallium arsenide case is slightly challenging. People started to produce in terms of quantum dots. Even silicon quantum dots are possible, but germanium is still the research is going. So now the hard topic is about another material which challenge these semiconductors, which is a perovskite. It's a mixture of organic and inorganic. Generally, the perovskite has a formula ABX3. This is the unit cell structure, and the size A falls on the corner of the unit cell, whereas the B will be in the middle, body center position, whereas X takes the face into the position. So in the case here, the X refers the halides, mostly the iodine, bromide, chloride, and the B is the well-established solar cell. What we have perovskite, how now it moved to tandem nearby 30, is made of lead. Now all the communities are concerned about lead and community, so they want to replace, and other alternative replaces tin. If you see the availability of these materials in the earth is still challenging. And methyl ammonium, formaldehyde ammonium, I think cesium, these are the other A compounds. And if you see the absorption coefficient of this perovskite, they are much higher. So that means the thickness you can reduce as much for the same efficiency of production. So some parameters, if you see the atomic coefficient is 10 power 4, then you can have a 1 micron. Likewise, if you have a 10 power 6 order, you can same thing, same order of efficiency you can have in 10 nanometer. So these are some of the parameters like responsivity, quantum efficiency, I discussed before, the basics of or characters of photodiode. I skipped this, the basic operation principle of photodiode. And basically, what is need is you need as much as with in the depletion layer or depletion region. You can ask me whether you need a heterojunction for a photodetector. No, we have a LDR, light dependent resistance, where there is a combination of semiconductor with metal. Metal won't absorb a light, so the possibility good of metal for photodetection. You need a semiconductor. Just a thin film with a ohmic contact is sufficient to have a photodetector, but the efficiency will be very low. So in the case of heterojunction, what happens is in the depletion region, once the light is absorbed, light will be absorbed in all the forms, in the P type, N type, and the depletion region also. In the other case, so the chances, that is the carrier lifetime will be very, very less. So they will recombine much faster. Mostly the carrier lifetime will be the out of less than nanoseconds. So in the case of depletion, it will drift. It depends on the barrier potential or the building potential. So the carrier will move to the respective anode or cathode. So the efficiency will be higher when you take a heterojunction. So now the technology in the solution process, you can have, only thing is you have to make a proper dispersed solutions of your precursors. You can find various ways, spray coating, spin coating, inject, blade after blade, or drop casting, and so on. I just indicated here only the few normally do in the labs. And these are in the case of photo detectors, you can cover the entire range, to be frank. You can start if you are working on organic semiconductors, dyes, perovskites, quantum dots. You can tune from the X-ray to even nearby the high IR. So there are around 3000 nanometers. So each has its own applications. Must we will most of us will stick with the UV and visible, and very few will go for the IR, the common research. Other than in the industry, they will go for even the X-ray part and the other for X-ray and the remote sensing needs also be there. In the middle IR, night vision cameras where we use has need a photo detector for IR cameras and spectroscopy applications. So in this, the performance matrix of some of the solution process to photo detectors that are recently developed, you can compete with the commercial available compound semiconductors as well as the silicon and germanium semiconductors. Their directivity range, for example, in the case of say the carbon quantum dots, in the view visible range is up to the mark and the directivity of 10 power 14 joules. But as I said, the durability again the question to, and how to, the fabrication of device comes a question in the case of quantum dots mostly. And we all know that now we have quantum LED, mostly that's solution driven one. And the other, see here, the bandwidth or the frequencies where the devices can be operated with the polymer during the solution process. Then especially using perovskites can be compared with the other commercial one. And suppose if I want to use a detector where I got to have a broad range, like UV, visible, and NIR, rather than a specific wavelength. We used to say tandem, or you have to use a different materials. The solution process, one of the things that referred in the nature, like because you take a ITO and you have to have an electron transport layer Again, electron transport layer can be a semiconductor like I2O sources or FTO sources electron transport layer. Apart from that, to have a smooth interface, you can coat a aluminum doped Hydrogen or TaO2. Then you can have a perovskite quantum dots and bulk heterojunction made of polymers. Then you have metal contact to take that out. And these are some of the absorptions comparisons that covers for different materials. And for in the case this strategy is quantum dots will absorb most of the UV and visible, and the bulk heterojunction will of the polymer will absorb the IR, so you can compare the most of the spectrum. I'll skip this. I think the time will not be sufficient to discuss much more about perovskite here. The same idea has been done and researched by using a PME for conducting this a substrate where you have a cathode and you have an anode by metallic contacts and bulk heterojunction and perovskite quantum dots for observing a wide range. So majorly in my lab, we use nanostructures mostly of ZNMO, and as you all know, the ZNMO is one multi-functional. You can easily grow different forms of nanostructures. And one of the solution process we normally call as hydrothermal, and it was later, since the pressure is not sustained much more, we call this aqueous solution process. We just to take a zinc nitrate and examine, you know, it's a cage like structure which will control the formation of OH when the temperature will increase by dissociating into ammonia, that lead to reaction with the zinc cation and forms the zinc oxide. And the primary thing in this process is you have to create a seed layer, and the nature of the seed layer will dictate the growth. And you can see our grown nanorods here. It's been broken, so you can see the cleaved substrate. You can see the broken nanorods here and there. The parameters are well established now. You can use ordinary lab oven. Initially, it was grown for hours, for 10 hours. Now it was reduced to 4 or 2 hours. Depends on the length of you need. And the seed layer depends whether you can, if you have the feasibility, you can grow by any solution process. In our lab, we use all solution process by means of spin coating. We create a zinc oxide layer. In most other cases, they use sputtered ZNO as a seed layer, and you can take just a dip ZNO as a seed layer too. And since both process they want to establish growth mechanism, we also tried our best to go for analysis in terms of establishing the growth mechanism. And our interest in the influence of seed layer, it was a long before, probably 15 years before. So if you see the seed layer, we grown this with a simple solution by taking zinc acetate and methoxy monocarbonate stabilizer. We coated for we ate the solution and coated by spin coating around 3000 RPM. We did in a different substrate like glass, silicon, and even sapphire L2O3. And you can see that with the room family to need form a ZNO 150 degrees Celsius is sufficient. If you go beyond that, you can increase the width. And we just increase the here, if you see here, we increase the grain size of the seed layer by annealing. The grain size are annealed, and we studied the influence on the growth of a nanorod. This is the picture. It shows the growth. Actually, as I told, the mechanism to be established. These are some pictures of the seed layer, and this is the 13 minutes after the growth in the solution, and 2 hours and 4 hours. And you can see how the rods are being evolved and nucleation being there. The process is a little bit slow if you compare other process. Nowadays, we change this method from the lab to microwave, where the domestic microwave can grow in many minutes. So 5 to 7 minutes, we can be able to grow in terms of 500 nanometer rods length. The average diameter will be around 30 nanometer. So these are the what we observed is the seed influences much more in the diameter of the nanorod as well as their density. You can see the density that depends on the if the seed layer doesn't as much pores, then the nanorod zones will also will have probably not there in the particular pores. Will get affected. Major forms and mechanism is this 001 plane will Android will have a higher growth rate compared to 100 plane. So if you are able to the seed influence the 001 growth, so we get a nano wire growth. These are the XRD and photovoltaic. I'll skip this. This. To come to the device, we use this digital effectively to form photo detectors. Major theme of my research in terms of the solution process P-type semiconductors. So problem is P-type is not stable. So we move around and we all know like the copper compounds, the copper oxide, copper sulfide. And one we took is a copper iodide. The vacancies of copper in the immune cell will create excess hole carrier natively. So that forms a P-type. And we just took copper iodide and dissolved in acetonitrine and import it in and heat it in different atmospheres. We find we heat it in argon atmosphere, probably at low temperature from 150 to 250 degrees, not at the high like 800 or 400. But the iodine deficiency is more. We observe that after 200 degrees Celsius there is an iodine deficiency being formed, and this iodine vacancy is more in the photoluminescence spectrum. So when you increase the anion temperature, as expected, the growth range will increase. And what influence here in the case of copper iodide, we have a particular aligned growth. One-on-one plane has a faster growth rate compared to the other, as discussed in the nanorods too. So other vibrational studies are being studied, and one match what is whenever we take these halides, they are easily tend to form an oxide. So we, if there is a presence of amorphous oxide that will cannot be detected in the case of characterization, so we use Raman spectroscopy to check whether the copper oxide presence is there. Fortunately, we don't have those. And we studied the transmittance. The transmittance will be a parameter when you want to have transparent P-type semiconductors. So we able to achieve up to 80% transmittance. And the band gap of the semiconductor is around 2.95 eV, and not much smooth. When we grow, we can could able to see visible here. I found the AFM micrographs of if you go for SEM, we could see a lot of pores. Still, the solution process in this material has to optimize. Even though more devices started to come in this, as a part of measuring for devices, the primary to know about the carrier concentration. One way is to go for Hall measurements, and we successfully creates a P-type. That's what we found in the Hall measurements in the order of 10 power 18. But the mobility is a factor that still has to be much. It is in the order of 10 power minus 1. And that is in the PL, we could able to see there is a copper vacancy is there near to your band edge emission. There is that band gap for emissions. And so we took copper rated as a P-type and the nanorods for an N-type. And this is the growth process, what we did systematically. And we form a heterojunction. This is the TE micrograph for you. And whenever we say heterojunction, it should be attached properly. We had an issue initially when the copper iodide was coated above, like I shown here. It was attached one not uniformly throughout, not forms like kind of a forcing structure. It is attached here and there. And so to analyze further the interface between the xenon and copper iodide, we took SAED and simulation to form how the orientation of the xenon at the interface and the copper iodide on the interface. And we change the growth process. And when we see the band alignment, and when we go for the band structure, there's a huge variation in the conduction band edges of ZMO and copper. So we introduce a zinc layer, sulfide layer in between them, and reduce the difference in band edge. And you can see there we use STEM to for redax for analyzing the introduction of sulfur, and the presence of oxygen and sulfur was confirmed, and the diffraction studies also we performed in the CD to confirm that. And this is a simple schematic diagram of the device what we have done. And since it is the band caps are around 2.9 eV, in the both the ZNO is 3.2, and I think you also can absorption study. It's all comes here by UV. We took a UV detection photo detector process. And this is the dot, the ID of the device what we have applied in our lab. And these are the photo response characteristics of our devices. As I said, the bare human Israel can have a photo detection ability, but you can see here the photo current started to increase in the order of 10 power 3 when you have forms and interface. And when you insert zinc sulfide, we could able to even use very less interns. Actually, the intensity what we use is 0.25 milli in terms of micro watt. And we studied the photo response characteristics, and it is in terms of hundreds of milliseconds to respond. It's okay, not being you can't commercialize this. You have to have it in terms of less than 10 orders of milliseconds or microseconds in order to commercialize. And this is a band alignment of the photo directions what been discussed before. All are solution process, and we directed for different one of the way to characterize your devices. One thing is stability, and you should not always report with one device. You have to check for multiple device and take an average report. Most of the journals now they are asking this, and these are with a different light intensity. And one more thing, what we do, this is since I told us UV detector, we check for the whole range of UV, the different LEDs whatever are available with us, and visible too. And we found that it's mostly 360 nanometer is more responsive, and it is higher for our devices. And this is the comparison of our devices, solution process device with others, which has been done in different techniques. And one thing, what we did is here, our device are what we call as externally, we no need to supply voltage. Normally, the photo detectors, commercial photo detectors, we need a reverse voltage to be given to increase the detectivity. And now, due to this nano arrangements, we could able to have a self-powered devices. Unless you don't need to give a voltage, 0 volt is being given for all the detections. Other material we develop, another p-type is bismuth copper oxysulfide is natively it is a layered form. So it forms electron confinement in the structure itself. So it leads to our advantage in terms of photo directions. And one problem is in the solution process, it's very difficult to synthesize this material. And other methods are still developed. One is you have to fuse between the parts, and you have to develop with a high heating and high temperature conditions in the closed atmosphere under vacuum. That too, you can only still the flames are not reported. And our group and other on Chinese group so far has reported the flame formation of this complex. And we just synthesis the material by hydrothermal, and we optimize the growth for different hours, different temperature, and finally with the XRD and Raman we found the proper material has been done, and we studied their valence and occupation states, and because always it has an impurity level, bismuth sulfide, bitumen oxide being always found. we took XPS to confirm the proper formation of bismuth copper sulfide. And we sufficiently used the TEM analysis for the bismuth copper oxide particles. And you can see there, we could be able to get a particular pattern where we can able to check all the atoms in the lattice. In the TEM, there is an axis what we refer as a zone axis. Within the zone axis direction, if you are able to view, you can able to view most of the planes in that the direction is passing through. So along the zone axis, you can able to view a particular plane where you can change it also. It depends on the zone axis. The occupation of atoms in the lattice can be visualized. So here, this is a kind of a simulation what we did for understanding the particular zone axis. What are the atoms that are present in the HRT image? So this is the bismuth, copper, and oxygen sulfur. And copper actually, to be frank, is not visible here. It is simulated along. It will be visible along 100 direction. That we could be able to go through for 100. We took in 001 and 010 axis. And what we did is, since this is a solution process and very difficult to form the synthesis, when we checked for the Hall measurements, the carrier mobility and the is slightly doubt, it's a higher or range, but the carrier concentration is very low in the part of intensity. So we couldn't able to fabricate as such PN device which we did before, which we were taking N-type ZNO and copper data P-type. So our plan is slightly varied. So we, since the bank-up of the material is around 1.1 EV, so we thought that this will be like the silicon, this will be a good absorber. Their lattice and the electronic structure also supports that. So we took a heterojunction formation. We took an N-type in the order of 10 power 18, and we just drop casted the synthesized bismuth copper oxide sulfide with a spherical PVA. Covered the silicon of 2 × 2 centimeter in maximum. Mostly we did with 1 × 1 devices, and coated copper iodide over it to have a higher efficient P-type character. So this, as I skipped the PIN junction, maximum absorption of the depletion region will be enhanced with the introduction of intensity layer in the depletion region. So this addition to the heterojunctions in the N and the intrinsic as well as P and intrinsic, the intrinsic layer will have a maximum width of absorption. So since it is a maximum needle, the width will increase because of a process. We got around 7 micron thicknesses, but we used that effectively for our advantages. And you can see here there is a difference in the reverse bias with the light and dark additions. This too, we did analysis for self-forward, and we did with the different ranges. To start with, we did with the red light of 620 nanometer, very low intensity and slightly intense intensity too. We could be able to achieve a photocurrent of nanoamps, not like microamps in the previous cases. The responsibility of this device is okay. Detectivity is in the order of 10 power 12 joules. We could be able to check the repeatability for different on and off cycles for thousands of more. And what we have been seeing is, apart from the photo detection, when we change the incident light from red to IR, say 850 nanometer, we could observe another peak here. This is an additional behavior that happens in the material, where the IR, when it observes, that will create temperature difference in the material, and that lead to flow of electrons from the hotter region to the lower region, and for the time where there is a temperature difference or temperature gradient that exists within the material. So we call that as a pyroelectric effect, and we could able to observe the pyroelectric current in the intrinsic layer of this copper oxide sulfide, and we check with the bare silicate too. So here, if you see here, what the advantage what we had is compared to the previous stage, we could be able to extend the selectivity. That means we can able to not only the UV detector, we started from the RIB and we moved to 850 nanometer IR. It shows probably a considerable reduction in the IR. And if you go to moving to UV range, it shows the detection, but it's very, very minimal. So this detector has sufficiently covered the part of most parts of the visible region and part of IR. So we referred as a broadband detector. So just this is not too restricted with our work. There are a lot of solution passer devices now available, especially if you see the South Korea. The devices, whatever comes from them, is mostly solution passer devices. In the case of semiconductors, you can easily fabricate the thin film transistors. I think probably you all know what is thin film transistor. We had a previous before LCD displays, then we had a thin film transistors which are supported of back LED now. So this thin film transistor displays are can be done with the solution process. And our group is started to explore those devices here. It's already in the market too in some of the devices. And quantum dots, solution process is nowadays by injection process. Most of the quantum dots are being done. And as I shown before, few papers, one or two papers of Nature in perovskite quantum dots. Even though largely I didn't discuss about the synthesis process, device possibility for this is much more. Not only in the case of solar cells, but other part of the devices like photodetectors, these are well established, especially the cesium like the iodide and cesium replaced, just like can be replaced by another. One issues with this perovskite is the stability. If they are mostly halides, when they are exposed to moisture, temperature, and other like even UV, this they tend to deteriorate in time. In the commercial cases, they are enclosed or embedded with a polymer in order to not to react with the fire moisture. So still devices are there, like how our LEDs are there. We have an LED and it will be polyacromide disclosed above the LED for our techniques. So most now you can do, but with a limited facility, the device can be processed with the solution process. We need not to be always worry about the chemical vapor deposition and other higher temperature needed for the growth of devices, especially the detectors. And these are my groups. Sham, most of the work what I presented here is part of this PhD thesis in our group. And Anilakshmi is recently joined in the group, who is also working on P-Tech semiconductor, basically on thermoelectric properties. With this, I stop my presentation. If you have any doubts, please.
Yes, sir. Yes, sir, thank you. Thank you, Professor Ramu Subramanian, for sharing more number of metal combinations for doping with for semiconductors. It was a highly informative session what we have today. Now the forum is open for the discussions. Participants can raise their queries. I think in between the session, somebody has raised their hands for asking somebody something about the session. If you are there, please you may make the question. You may raise your question, sir. I think Satya has raised his hand. Is there? there any other queries? The forum is open for discussions. Okay, we congratulate the research team for Arasu, sir.
Thank you, sir. Thank you.
Yes, sir. Thank you. Somebody is joining. Okay. It was a wonderful session, sir, what we had today. It is highly informative. Thank you so much. I invite Mrs. Parimala, Assistant Professor, Department of Chemistry, to deliver the vote of thanks.
A very good afternoon to all. It gives me great pleasure for proposing vote of thanks for the FTP on the title of Simple Solution Processed Semiconductor Device. I render my heartfelt thanks on behalf of our management and our department to our resource person for sharing his insight on Simple Solution Process Semiconductor Device with us. I hope all the participants had a great and informative session. Thank you all.
Thank you, ma'am.
Thank you.
Thank you very much. The feedback link will be shared now on the chat boxes of both Google Meet and YouTube chat boxes. It will be available for 5 minutes for you, and we receiving the responses for 15 minutes. Okay. Thank you all and all join together today. Thank you very much. Yes, sir. Thank you very much, sir.
Thank you.